While we want to be able to identify the soil horizons, we also want to be able to describe soils just in an objective way without inferring how the soils got that way. And we'll also be interested in applying the same descriptive techniques to materials that are below the soil horizon per se, that are below the B horizon, for example, and just be able to describe these materials in an objective way. And so, to some extent, what you can describe depends on what kind of samples you have. And there'll be three main ways that the samples will be obtained. One is from a soil pit. And the advantage of having a pit is that it's a fairly large exposure. And here we see a soil pit, and we can see there's a contact between two soil horizons. And the advantage of having an exposure like this is that you can see lateral and vertical variations, and you can see structural detail. You can see things that vary, say, over the scale of a meter. One of the downsides, though, is that it's hard to make these pits very deep. And so if you're interested in what happens down several meters, it's possible to do that, but it gets to be quite expensive, or at least fairly rare where you come across these exposures. You can also take cores of soils. Here's an example of a core that's obtained by hand, and this is a split spoon core. Split spoon cores can be obtained with a drill rig, and so you can get them from fairly great depth. Also, there's a possibility of getting a sample with an auger. Now, the advantage of using a core is that you can go into the subsurface and you can get some of the soil that's relatively intact. So you can see the layering. You may be able to see some bedding if it's deposited as an alluvial material, for example. And so that's an advantage. The problem, though, is that it can be difficult to get a sampler like this through the soil. If there are rocks or caliche, it can be difficult. And so you may also just not be able to reach deep enough with these cores. It also may be that they're just too small to see what you're interested in. This auger is another possibility. Augers are what you use to make a borehole with. This could be an auger that is on a drilling rig, or it could be an auger that's used by hand. In both cases, you can bring material up from depth, and you can characterize that material in some respects. Now, the auger will generally disrupt the material, and so you can't really see bedding or the structure of the soils. But you can certainly get the material, and you can characterize the color and grain size. And so samples obtained in that manner can be valuable. This is a list of the main characteristics that are generally used for describing soils. The density and consistency, color, classification, and so on. And so let's take a look at those in a little more detail. So there are several different classifications for soils, and the two main ones are by the USDA and by the so-called USCS, or United Soil Classification System. The USDA is based on the size fractions of the different materials. So soils have sand, clay, and silt. And so the soils will have some fraction of those three end-member grain sizes, and there'll be mixtures of them. And so the USDA has come up with different classifications based on the fractions of these three end members. And a type of soil that has a fairly even distribution amongst these three is a loam. In the USCS, this is another approach. It uses it looks at the grain size, where you have coarse grain materials that are sands and gravels, and then for fine grain materials, it looks at the plasticity, and it defines low, medium, and high plasticity, And so this allows you to subdivide the fine grain materials based on how plastic they are. Generally, the degree of plasticity is a pretty good indicator of the clay content. And then also another uh, large classification scheme is the organic content of the soil. So the USCS uses whether it's coarse grain or fine grain and the organic content, and then it can further subdivide it from there. So there are a variety of schemes for coming up with or for sort of guiding the description of soils. Once you're experienced with this, you know the schemes, but while you're beginning, it's useful to have a guide so that you can make sure that you are getting all of the characteristics, and the guide could also give you some structure to how you go about making the descriptions, the various subclasses and so on. And so this is a guide that's made by these guys here, Midwest Geologic, or Midwest Geosciences. Here's their name. And this is quite a convenient sheet that's laminated, so it's made for field use, and it has the different characteristics over here. So it kind of leads you through the steps that you would take to describe the soils, starting off with the density or consistency and doing the color, and then so on. And then while you're, say, doing the color, you go and you look at this structure, and it says, for example, is the color a matrix color? And if it's yes, then you go up here and do this, and if it's no, you do that, and so on. Okay, so this is a helpful thing. We have quite a few of these sheets, and we'll use these in class. There are a variety of others out there, and so if you search around, you can find other things like this. This ends up being something that we find convenient and will utilize in the course. Okay, so what I'm going to do is go through this list, starting with density or consistency, and take a look at these characteristics. So these are the different types of consistency, loose to extremely firm, and this will depend on the moisture content, the cement, and so you can get a different result if you depending on what the water content is. One of the ways that this is determined in a fairly objective way is with the SPT, the standard penetration test. And this is done when you're getting samples with a split spoon sampler, like I showed you a couple of slides ago. And in that case, you use a standard hammer, and it involves dropping a weight. That 140-pound weight is usually what's used, and the N value is the number of blows, the number of time the 140-pound weight is dropped on the sampler in order to drive the sampler in by 6 inches. And so you have an N value for the first 6, the next 6, the next 6, depending on how long the sampler is. So you would get a series of these N values, and through the years people have written down these N values and correlated them to different size or different consistency of soils. So you can match up the standard penetration test N value with the consistency of the soil. Another way to do it is to measure the compressive strength or the shear strength, and there are a couple of ways of doing that that are shown here. These are field techniques. You can send the soil to the laboratory and also make these measurements, but for a lot of what we're doing, we're particularly interested in what can be measured in the field. This is one device, a pocket penetrometer. It measures the unconfined compressive strength, and the vane shear tester, this measures the shear strength. So here's how these things work. The pocket penetrometer, this piece right here, that's just a cylindrical tip, and that's pushed into the soil. This cylinder here goes back into the handle, and there's a spring. And so when you push it in, the cylinder gets compressed, and the harder you push, the more it gets compressed, and the more force is exerted. And so what you do, it's hard to see, but right there is a ring on that cylinder. It's about a quarter of an inch back from the end. And so you clean the soil off so it's a relatively flat surface, and then you push this in so that it embeds it by 1/4 of an inch up to that groove. And this ring here is pushed all the way up flush with this piece. And so as you push this in, this piece here gets pushed into the handle, and then when you take it back, it springs back out, but this ring gets left behind. And so the location of that ring on this shaft here tells you the maximum amount of force that was done right at the end of the push. And so that then can be used to get the unconfined compressive strength. Typically, the shaft here is just graduated, and you can read off the unconfined compressive strength directly. The vane shear tester, there are several of these devices, and this is a kind that we'll use in the field. And it's, well, these are the vanes here, and you can see there are various different discs, different sizes, different patterns of vanes, but they're typically these radial plates, and these things are attached onto the end of this piece right here. And you can see the spring. And in this case, what happens is this piece is put on the end and then pushed into the soil. And you can see this is being done on a hand sample. And so it's pushed in the soil, and these vanes are embedded into the soil. And then this handle is rotated, and there's a spring here, and it's rotated, and as it rotates, the spring, it takes up some tension, and eventually you have enough torque applied to this handle so that the soil breaks away and shears right here at the top of these vanes. And this dial here is arranged in a similar style to this ring. So there's a little indicator right here, and as you rotate this, it advances the indicator, and then when the soil fails, the spring retracts this and it unwinds, but the indicator is there to tell you the maximum amount of torque that was applied right at the time of failure. And that is used then to determine the shear strength. Okay, so it's a simple test where you can measure shear strength by pushing this device and twisting it in the field. And then if you have these data, the shear strength or the unconfined compressive strength, then you could use tables like this one to determine the consistency of the soil from very soft to hard materials. And notice that this is in PSF, that would be pounds per square foot. So you need to check and see what units these devices are giving you and make sure to convert to the appropriate units for the table that you're using. Okay, so the soil texture classes, these are the classes that are used by the USDA classification scheme. And we have a trilinear diagram that shows how they work here. This diagram has the three different grain sizes, clay, silt, and sand, as the apex of the triangle. So this one is clay here, sand, and silt. And so what's done is to get a sample, well, one approach that can be done is to get a sample of soil and put it in a sieve like this one. And each one of these pans right here has a sieve at the bottom of it, and there are, I guess, about 6 or 7 of these. Each one has a sieve of a different size, and so you shake it and the soil goes through these sieves, and then you weigh the amount of soil that's retained on each one, and that gives you a size distribution. When you get down to fine material that's, say, very fine sand or silt, and then you want to determine how much what the silt and clay fraction is, you generally have to use a different technique where you suspend this fine-grained material in water and allow it to settle out, and the rate at which it settles out depends on the grain size, and you use that process to determine the fine grain fraction. Okay, so that's one way to determine the fraction of sand, silt, and clay. And if you were to do that, for example, and you had a little bit of silt and sand and clay, say about 20%, say 80% sand and 20% remaining split between silt and clay, then it would work. It would work like this. So the sand fraction is given by these numbers, and so 80% silt or 80% sand would be right there, and then if it's equal fractions of silt and clay, then it would be halfway along between these two boundaries. If it was let's see, if it was 90%, yeah, well, let's try another one. Let's say we have sand is 0.4 and clay is 0.2, and silt would be 0.4. So the clay fraction, let's see, let's do sand first. Okay, so we go up from here to get the sand fraction, so sand would be along there. Clay is going to be up along this axis, and we have 0.2 or 20% clay, so it's going to be along this line right here. And silt, these things have to add up to 1. So silt is going to be, here's the silt axis. So there's, right there is 40% silt. So we go along this axis here. So they intersect right at this point. And we see that that plots in this field that that's a loam. So if this is the size fraction, we can use this trilinear diagram to determine what the texture class is, and in this particular example it would be a loam. Okay, so fair enough, we can see how this works. One of the problems though is that if we were to do this, we would have to go through this sieving process. That requires going back to the laboratory and drying the soil out and then doing the sieving. And then we would also have to go and do this hydrometer test, or a test, some other kind of test that determines how much silt and clay fraction we have. You generally can't tell the difference between those two just by a sieve because the materials are too small to be sieved accurately. So this works. It works great, but it requires laboratory techniques, and so we need to have something that is a little bit easier to do in the field for this to really be practical. And I'll show you in a second how to go about doing that.